In situ soil washing is a remediation technique that involves injecting a washing solution, such as water, surfactants, or chemical agents, directly into contaminated soil to dissolve, desorb, or mobilize pollutants. The contaminants are then flushed out and extracted for treatment, leaving the soil cleaner without excavation. This method is particularly effective for removing heavy metals, petroleum, hydrocarbons, and other soluble contaminants from permeable soils. In situ soil washing works by mobilizing contaminants so they can be extracted from the soil. The process relies on three key physical mechanisms: dissolution and desorption, in which the contaminants dissolve in the washing solution or detach from soil particles; mobilization and transport, in which the solution carries the contaminants through the soil toward an extraction well; and dispersion and dilution, in which the spreading of the washing solution reduces the concentration of the contaminants. This solution occurs when water or a washing solution dissolves contaminants, making them mobile, and desorption happens when contaminants detach from soil particles and enter the washing solution. The factors affecting dissolution and desorption include contaminant solubility. For example, water-soluble contaminants such as salts and some metals dissolve easily. For soil composition, organic-rich soils hold contaminants more tightly, requiring stronger washing solutions. And finally, pH and chemical environment also affect dissolution and desorption, as some contaminants only dissolve in acidic or basic conditions. Mobilization refers to the process of making contaminants move from the soil particles into the washing solution. Mobilization of the particles is done by the two previous mechanisms, dissolution and desorption. Once the contaminants are mobilized, transport involves carrying them through the soil and into an extraction system. The washing solution moves through the soil, picking up contaminants along the way and bringing them to the extraction well or surface for further treatment. So basically how it works is a washing solution is first injected into the contaminated soil. As it percolates through the soil, it picks up contaminants, and then the contaminated solution is then extracted and treated. This simple diagram of the system can help to visualize mobilization and transport. On the left-hand side of the figure, we see the washing solution being inserted into the groundwater. Moving from left to right, it flows through the contaminated soil, bringing all the contaminants with it. Once it reaches the extraction well, a pump sends it above the surface, where the contaminants can then be collected and treated further ex situ. The first factor affecting mobilization and transport is permeability of the soil. The ease with which the washing solution moves through the soil depends on the soil's permeability. In highly permeable soils like sand or gravel, the solution moves freely, making the transport of contaminants more efficient. However, in lower permeable soils like clay, transport is much slower, requiring more time or additional measures like fracturing the soil to create pathways. The flow pathway also affects the mobilization and transport. Water or the washing solution follows the path of least resistance in the soil, which can create preferential flow channels. This means that some areas of soil may be treated more thoroughly than others, leading to uneven contaminant removal unless the flow is well managed. Another factor affecting mobilization and transport is the hydraulic gradient. The pressure difference between the injection points where the washing solution is introduced and the extraction wells drives the movement of the solution through the soil. This can affect the speed and effectiveness of the transport process. And the final factor is capillary action. In finer-grained soils, capillary forces can make it harder for water to move through, which can slow down transport. However, in some cases, this can also help retain contaminants in the washing solution if the flow is slow enough. Some challenges to mobilization and transport is, first, the soil composition. The presence of organic matter, clays, or fine particles can reduce the efficiency of mobilization, making contaminants more strongly bound to the soil. Incomplete treatment is another challenge. In soils with heterogeneous permeability, contaminants may be left behind in areas that are difficult to reach by the washing solution. This is often referred to as the channeling effect, where the solution preferentially flows through certain parts of the soil, leaving other areas untreated. And the final challenge is contaminant behavior, where some contaminants, like hydrophobic substances, require additional agents, such as surfactants, to effectively mobilize and transport them. Dispersion is the spreading out of contaminants as the washing fluid moves through the soil. It happens because of 1. The difference in flow velocities, as some water moves faster and some moves slower, and 2. The twisting, turning, and splitting of fluid around soil particles. Dispersion helps reduce high concentrations of contaminants in one area, distributing them over a larger volume. This doesn't remove the contaminants, but it makes the site less toxic in concentrated zones. Dilution is the mixing of contaminated water with clean water, usually from the washing solution or surrounding groundwater. This lowers the overall concentration of the contaminants. Lower concentrations mean contaminants are less harmful. It's easier and safer to treat at the surface after extraction, and some regulations allow for natural attenuation, which is letting diluted contamination degrade over time rather than being treated. While both dispersion and dilution may reduce hot spots of contamination, neither of them destroy or remove contaminants alone. Drawbacks include for the potential spreading of contamination to previously clean areas if not controlled, and they may create a false sense of remediation. Just because concentration is lower doesn't mean the site is clean. Different contaminants respond differently to soil washing. The influencing factors tell us how the contaminants will respond differently to the soil washing. There is some overlap between the influencing factors and those affecting the physical mechanisms as previously described, such as contaminant properties and soil permeability. So for contaminant properties, highly soluble contaminants like salts and some metals are easily removed with water alone, whereas slightly soluble contaminants like petroleum hydrocarbons or PAHs require surfactants or chelating agents. And hydrophobic contaminants like PCBs and heavy oils are strongly absorbed to the soil, making them difficult to remove. Soil permeability is important because it controls how well the washing solution moves through the ground. Sand and gravel has a high permeability, making it the best for washing as it allows the solution to move freely. Silt, having a medium permeability, still allows the solution to move freely, but much slower than sand or gravel. And low permeability soils like clay is the worst for soil washing, as the solution can barely move through it. As a result of low permeability, treatment times can be longer and fracturing the soil may be required to create flow paths for the solution to move through. The presence of an aquiclude can either help or hinder remediation. As an impermeable layer, an aquiclude can stop contaminants from migrating deeper into groundwater. However, it can also trap contaminants, making them hard to extract. The washing solution may also end up pooling above the aquiclude rather than moving through the soil. And finally, the chemical properties of the washing solution can also affect how well contaminants are removed. Acidic solutions help dissolve heavy metals, and alkaline solutions break down hydrocarbons. Chemical additives like chelating agents are also added to help mobilize contaminants. These agents bind to metals, reduce surface tension, and can change ion exchange conditions in the soil to release bound contaminants.
The objective of in situ soil washing is to detach and mobilize contaminants that are bound to soil particles. This is done by injecting a washing solution into the ground. The washing solution will reduce the bond between the contaminant and the soil, allowing the pollutants to be flushed out and collected for treatment. This method is particularly effective in targeting contaminants located in the soil pore spaces or contaminants that are weakly absorbed onto soil surfaces. A major advantage of in situ soil washing is that it treats the soil without the need for excavation, which greatly reduces the effect on the surrounding environment. This makes in situ soil washing well suited for sites near any sensitive areas. Some examples of sensitive areas are residential zones, wetlands, or operating facilities. In situ soil washing also helps to preserve soil structure, limit carbon footprint, and reduce long-term site restoration needs. Beyond contaminant removal, in situ soil washing aims to restore the functional use of the land. Once clean, the soil can safely support vegetation, wildlife, or redevelopment, depending on the end-use goal. For industrial or brownfield sites, it helps prepare land for reuse or redevelopment by removing toxic legacies. In agricultural areas, it can allow for the safe return of land to production, especially when heavy metals or fuel residues are the primary pollutants. In situ soil washing is designed to meet site-specific cleanup goals based on the national or regional environmental standards. These may relate to soil concentration thresholds for certain contaminants, groundwater protection criteria, or risk-based exposure levels for human and ecological receptors. Monitoring and sampling throughout the project verify that the cleanup has been achieved and that regulatory compliance has been achieved. Some of the contaminants that in situ soil washing can treat are aromatics, halogen-based solvents, fuel oils, heavy metals, and PCBs. Stages of implementing in situ soil washing are site characterization, design and planning, installation of equipment, injecting and flushing of washing fluids, extraction of washing fluids, and post-water treatment. Characterization. Site characterization forms a scientific foundation of the project. Engineers and geologists will investigate soil layers to determine if they are conducive to washing. For example, sandy soils allow for easier fluid flow, while clay-rich soils can resist flushing and groundwater flow. Understanding where and how deeply the contaminants are distributed helps design targeted treatment. Hydrogeological studies are critical because the proposed soil washing process must not unintentionally spread the contaminants. Some hydrological studies that could be done are bench scale tests. Bench scale tests simulate soil washing in the lab using site samples to evaluate how well the contaminants respond to different chemical agents. The data from the bench scale test will help determine if in situ soil washing is a viable technique and is economically feasible. Design and planning. Based on tests, soil samples, and contaminant characteristics, a washing agent will be selected. Some examples of washing agents are surfactants for organic contaminants like diesel, or chelators for heavy metal contaminants like lead or arsenic. Fluid flow is modeled to predict where the washing solution will go and how fast it will travel through the soil. Safety is also a focus. What happens if chemicals leak or if mobilized contaminants reach a sensitive receptor like a drinking water aquifer? Plans are prepared for those scenarios and permits have to be obtained to inject and extract fluids. Installation. Once all the permitting and planning has been completed, installation will begin. The in situ soil washing system is physically installed at the site when wells are drilled down to the contaminated zones and fitted with screened sections. Injection wells will deliver the washing solution, and extraction wells will collect the contaminated fluid and pump them out of the soil. Tanks and pumps are placed on site, often within a contaminated berm. Portable treatment units, such as carbon filters, oil water separators, or chemical dosing systems, are connected and put on site for cleaning the extracted fluids. If there are no treatment units on site, the extracted fluid can be sent to a treatment facility. Monitoring wells with instruments such as flow meters, pH gauge, electroconductivity gauge, and contaminant sensors help track how the chemistry and contamination of the soil are changing underground from the in situ soil washing. Injecting and flushing. Injecting and flushing is the active remediation phase of in situ soil washing. Washing solution is injected into the soil under pressure. The chemistry of the washing solution is designed to loosen the contaminants from the soil particles, whether by dissolving them, altering their charge, or breaking their bonds. Flushing cycles are managed to maintain flow without causing excessive pressure or hydrofracturing in the soil. Monitoring wells are used to help observe the breakthrough of contaminants at different locations. The system can be adjusted in real time for instance, by alternating injection/extraction wells or varying chemical concentrations in the washing fluids. Water treatment. Once the contaminants have been mobilized by the washing fluid, they are recovered with the extraction system. An extraction system is usually an extracting well. The contaminated fluid goes to a treatment train. A treatment train consists of numerous numbers of water treatment technologies. A treatment train often involves settling tanks, filters, pH adjustment, oxidation, and/or adsorption systems. The exact treatment train will be dependent on what contaminant needs to be treated. Heavy metals are typically removed via precipitation or ion exchange resins. Organic contaminants might require activated carbon or UV-based oxidation. If the treated water meets discharge standards after treatment, it can be released. Otherwise, it's recirculated to minimize waste. A case study. A real-world case demonstrates how in situ soil washing can be applied to hydrocarbon contamination. This site in Germany was contaminated by years of diesel leakage from underground storage tanks. Engineers used a biodegradable surfactant to flush contaminants from the soil. The system operated in 4-month cycles to optimize recovery while minimizing surfactant use. Groundwater monitoring wells were essential for ensuring that the mobilized diesel fuel did not escape the treatment zone. The final remediation efficiency was nearly 90%, and the site was cleared for light industrial reuse. This project highlights the importance of proper chemical selection, flow control, site management, and safety.
In this section, we will cover the demonstration level. 2 case studies have been picked out to highlight the use of in situ soil washing methods to treat contamination. The first site was a test in Delaware, while the second was a full-scale in situ flushing, which happened in Florida. So, the first case study took place in Dover Air Force Base in Dover, Delaware. Scientists from the Groundwater Remediation Field Laboratory conducted tests to release contaminants in a controlled manner and analyze the effectiveness of in situ soil washing methods. The soil type in this area was noted to be medium to fine grained sand with gravel, silt, and clay lenses. A known volume of PCE was released into one of the test cells. PCE is a challenging DNAPL to remove as it tends to sink into the water table and sit in the pores. After this, conservative tracer tests and field measurements were taken to predict the flow paths and find estimated porosities between 17 and 28%. The water table was located between the depths of 4.5 to 9 meters. In this test case, 12 injections and extraction wells were placed. 12 injection/extraction wells were placed throughout the cell, which is also shown in Part B of the diagram. When it comes to the implementation of the in situ flushing technology, 2 main solutions we will look at are the complex sugar flushing and co-solvent flooding. Complex sugar flushing involves a substance called cyclodextrin. The way cyclodextrin is structured is that it has a hydrophobic interior and a hydrophilic exterior. PCE is hydrophobic and is attracted to the inside of the complex sugar, forming an inclusion complex and trapping the contaminant inside. Using the 7-pore volume of cyclodextrin's complexation, 48% of the PCE mass was removed during the 90-day injection slash extraction cycle. In addition to this, an alcohol water co-solvent flood with 95% ethanol content was injected into the contaminated test cell. In the solubilization process, PCE dissolves into the ethanol and water solution and is pushed out through the extraction well. When effluent, this is the liquid with dissolved PCE. When effluent ethanol concentrations reached 65%, the waste was treated with activated carbon, then re-injected. This cycle continued for 40 days, yielding a final removal mass for 64% of the PCE using the co-solvent solubilization. Some main successes of co-solvent solubilization were high removal efficiencies at 64% in a decent amount of time. A failure, though, was the high cost involved for large quantities of remedial fluids, and that PCE in areas with low permeability were not fully removed. This could cause potential recontaminations of the aquifer in the long run, and is something to look out for. The second case study took place in November 1994 in Lynn Haven, Florida, under the Gulf Power Project. The use of arsenic-based herbicide caused a dissolved arsenic contaminant plume. Some details about the area were that the soil type was silty, fine sand, and the water table was 5 feet below the ground surface. Additionally, the confining layer was found at 25 feet depth. 14 injection/extraction wells were set up on the site. Citric acid was used as the primary flushing agent injected into the site. So citric acid is a weak acid, and it is able to bind with the oxidized state of arsenic to form soluble complexes. This interaction increased the solubility of arsenic in water. This interaction increases the solubility of arsenic in water and makes it easier to extract the contaminant from the soil during flushing. The effectiveness of this flushing agent is also dependent on factors such as the form of arsenic present and the existing pH of the environment. So as an example, in slightly more acidic conditions, citric acid works better at mobilizing contaminants. These are the reasons that for a toxic metal like arsenic, citric acid was injected for remediation. When the effluent was extracted, it was treated and a proprietary compound was supplemented into the flushing reagent and re-injected into the site to continue the flushing cycle. What were the results? After 6 months of treatment, 73% of arsenic was washed out of the soil. Some main successes that we see of citric acid flushing includes high removal efficiencies at 73%, and that the flushing agent was environmentally safe and is generally not toxic to be in the soils. Some failures that were seen during the case study were that there could have been a better integration between laboratory and field test work and implementing in situ soil washing on a full-scale site.
So for the application of in situ soil washing, it is particularly useful in situations where the contaminants are mobile and soluble, the soil is sandy or granular, minimal disturbance is required, and groundwater is a concern. For contaminants being mobile and soluble, this method is effective for removing heavy metals, petroleum, hydrocarbons, and other soluble contaminants that can be mobilized by washing agents. For the soil, high permeability soils allow for better distribution and recovery of the washing solution compared to other soils with low permeability. For minimal disturbance, since it is an in situ method, it will avoid excavation processes, which will reduce the environmental disruption and costs. And for groundwater, it can be integrated with groundwater treatment to prevent further contamination spread. So for example, application with an oil spill, getting a little look at a few things. First is hydrocarbon contamination. The fuel oil contamination can often be effectively mobilized using surfactants or co-solvents in in situ soil washing approach. And this method is useful for removing non-aqueous phase liquids, or NaPLs, if they are present in the subsurface. Along with this is soil permeability considerations. Like on the previous side, if the site has sandy or loosely packed soils, the washing solution can effectively penetrate and recover these contaminants. In contrast, clay or compacted soils may limit the efficiency of washing due to low permeability. Continuing on this, with the groundwater flow, the washing method must be carefully designed to avoid mobilizing the contaminants towards the town's water supplies. Hydraulic barriers such as pump and treat systems may be needed to prevent unintended migration. So following this, with the application of oil spill, there's also the regulatory compliance and cleanup timeline. So for example, let's say 3 years here. This method can then be effective within the given time frame if optimized for the site's hydrogeology. Continuous monitoring and potential combination with other remediation methods may be required to meet regulatory standards, and the cost may vary depending upon these situations. So we saw the applications, but there are also several limitations for in situ soil washing. One could be the soil permeability, which we saw for the application. Clay-rich or compacted soils, which have low permeability, makes it difficult for the washing solution to flow through and extract these contaminants effectively. The contaminant type also, strongly absorbed or hydrophobic contaminants may not be easily removed, which would limit the method's effectiveness. And for the groundwater control, it requires careful design to prevent contaminant migration and secondary groundwater pollution. Also, treatment and disposal of the extracted fluids, the recovered washing solution and mobilized contaminants must also be treated and disposed of properly, which can add to the project costs. And back to the design, site-specific design requirements. The method needs to be tailored to the site conditions, including the soil characteristics, hydrology, and contaminant properties, which can complicate implementation. And as you can see, a lot of these limitations go with the applications. Now, just like before, we had the applications and used oil spill as an example. There's a risk of contaminant mobilization. These washing agents can increase the contaminant mobility, which could potentially spread hydrocarbons into groundwater if it's not properly controlled. This requires careful hydraulic management to prevent migration towards drinking water wells or any other source of water that is used. Also, the soil type, if it has the high clay content, permeability will be low, which will make the washing process very inefficient. And the highly absorbed hydrocarbons may not effectively be removed from the fine-grained soils. Continuing on with some of these limitations, the complex fluid recovery and treatment. Extracted washing fluids will contain the hydrocarbons and other contaminants requiring the secondary treatment before disposal or reuse. The treatment of recovered washing fluids adds costs and operational complexity. Potential need for supplementary techniques. If the removal with in situ soil washing is not feasible for complete removal, additional methods like bioremediation or chemical oxidation may be required to degrade these residual hydrocarbons. As we saw and as stated earlier, the applications and limitations go together, but oil spill here is a good example as to how it is applied. So now on to the cost of in situ soil washing. I'm not going to go into a whole lot of depth on this slide, but we have the category, estimated costs, and details for everything. In categories, we have everything from site assessment and testing all the way to regulatory closure, which would basically be the lifespan of the whole entire project. At the same time, these projects will vary. This is a rough estimate to show the potential costs that may occur. So dependent upon different soils or land area in general, these may change. But ultimately, these factors that influence the cost are the soil permeability, the depth of contamination, regulatory requirements, and remediation additives. For soil permeability, as discussed before, the more permeable soils are cheaper to treat than clays because the clays have a lower permeability. The depth, deeper contamination needs more complex injection systems, rightfully so. And for the requirements, local cleanup standards can drive up costs. And the remediation additives, specialized surfactants, chelating agents, or pH adjusters can also add to the cost. So we saw the cost, but with that comes the availability. The in situ soil washing is less common than technologies like bioremediation, chemical oxidation, or pump and treat. This is largely due to the limited applicability to certain soil types. As seen earlier, we know in situ soil washing works best with lesser permeable materials or soils. There's also the need for specialized contractors and equipment for this, and challenges with the uniform reagent distribution in the subsurface also come up. Continuing with availability, we can see that in situ soil washing is a good fit with sites with shallow contamination and permeable soils, non-volatile contaminants like our heavy metals, PCBs, or hydrocarbons. And availability is a good fit also with projects that require minimal excavation due to infrastructure or ecological concerns. Thank you for listening to our presentation, and here are sources if you would like to look into anything any further.